Okay, so welcome back. Class 2. This week we'll start talking about, we did a little bit already last week about strings. We talked about how Python is organized, how Python, the language, actually organizes its information. The beginning of the class is a little programming heavy. The latter bits of the class are a little more physics, right? So we need the tools to actually start talking physics later. Again, if you want, I keep advertising these two books because I'm actually quite happy with them. So, if you want a extra book to read, then go grab those. The first Python syntax, and this week we do the second Jupyter Notebook. We do strings, lists, conditional statements, loops, and functions. So this is all the basic tools, like you're getting the toolbox full of hammers and screwdrivers and all that. Like this is there are no power tools in here just yet, but all the power tools are based on this. Yeah. So the strings was how we save the text. It acts like a list. So lists and strings are very closely related. They can be sliced. They can be substituted. They can be have several built-in useful functions like length and is-in and all those things. So you can just Google Python string functions, and there will be a long list of them. Essentially, you can do things like, if I have a really long piece of text, I can say, is my name mentioned in here, right? You can just do a little vanity project. You go like, is in, and you go, is in this long string, my name, for example. Lists can also be sliced, right? So slicing is that you take a subsection, a substring, or a sub list of a list. So you have your shopping list, for example, and this part is the dairy, right? So that's the milk, eggs, and butter. Sorry, that's usually my list. Anyway, so that's a sublist, right? So that's item number 8 to 12. That's a sliced list. It can be substituted. We're like, shouldn't put butter. So I'm replacing butter with margarine. So item number 13 becomes margarine. So I've replaced it in the list, yeah? I don't know, maybe none of you use shopping lists and just sort of go on vibes, but I have a shopping list because otherwise I forget stuff. Have several built-in functions. Again, same thing, length, substitutions, is in, that kind of thing. And the simplest way to define data, right? That was what we started with. If nothing else, you can start with a list of floats as your data, a list of text as your data. There are more complicated ways, and we are going to hit them soon. But it is the simplest way to just start with a list. Okay. Conditional statement is things like if statement is true, like if this is true, if the statement is the total statement. So this can be this is true, and this is true, and this is true, and this, all these conditions are met. Or you can say this is true, and this is true, or this is true, and this is true, right? So you can have this combination of logic gates. I don't know, some of you may have taken logic classes or philosophy. They're big on this stuff, right? It's like, if this is true and this is true, can I hold two conflicting thoughts in my head? Well, you might. Python will absolutely not, right? It will go, this is either true or false, and if not, then I'm not doing it. So if this is true, then do. If that condition is not met, then I'll do this. So this is everything else, all other instances. Elif is sort of like, if I want to do this and there's a subsection, then I go elif, elif. That can make infinite number of elif statements, although that gets hard to read and figure out what is when it goes into what logic gate. So the and, is this dying now on me? Yes. OK, fantastic. I'll use fingers. And or combinations are for that logic statement. And can be the text and an or, but you also have the ampersand or the straight bracket. So ampersand is and straight bracket is straight bar is or. That's another way. That's from C, if anybody remembers C++. But usually use and or because those are the English words, and you can actually just read it as if it's a statement. So if you have an if statement, it's literally, hey, is this true? Yes, go here. No, go there. The no go there is actually can be silent, right? You don't have to put an else statement in there. This can just be left off. This is just the rest of the program. If this is true, do this thing. For example, if clothes are dirty, do wash. You don't have to do an else. continue sitting on the couch, right? You don't have to put that in there. You can do nested statement where it's like, well, first if my clothes are dirty, need to go do the wash, right? But it's like, hey, here's a second statement that says, if I have detergent, yes, then go do the laundry. Or if I don't have detergent, then maybe buy the detergent first, right? So those are nested statement where you can go down the rabbit hole. I prefer this is sort of the length that I would advise you to use. Don't go any deeper, because otherwise it's like, hey, do I actually hit any of these final states? Do I actually execute all of them at some point, or is it just so when do you need these kind of statements? There's a version of this later where you do this for a whole list of numbers, and then it can be very, very useful. Okay, nested logic statements are, for example, I own a pizzeria. I love this one, so I just stuck it in. I own a pizzeria. Do they know about my pizza? Yes. Have they tried my pizza? Yes, right? So these are two different questions. These are yes-no questions. If I'm defining a research statement, or sorry, a research plan, or try to come up with a new scientific question, it usually is a good idea to break it down into yes-no questions, because you can break everything down in smaller and smaller questions, sub-questions, until they are yes and no questions. Okay, fine, yes, no, and but you know what I mean, right? It's usually, I would expect an answer to be yes or no here. True or not true. So, do they know about my pizza? Yes. Okay, then I am in one state where they have heard of me, but have they tried it? Yes. Okay, are they repeat purchasers? Yes. Okay, these are good customers. So this is my list. Suppose I have a long list of names of everybody who bought pizza, or no, I don't have that. I have the list of people that have possibly looked at my website, for example, or possibly just live in the neighborhood. I got the neighborhood mailing list or something. It's like, so these are questions I could ask them. The difference is like, hey, no, here's somebody I can send a flyer to, for example. I don't have to send them to these people. They've heard of us already. Or, no, they haven't tried. I can send them a coupon. So a different set of people, right? So you can actually start targeting different components by saying these yes-no questions. So you can do the same thing with lists. I'm running ahead of myself already. You can then target, for example, particular actions. Same thing in a program. So you can, for example, do like, they are repeat customers. No, I've lost them. These might just be people that don't like pizza and just made a mistake one day. But who are these people? So I can send them, I don't know, a coupon again to do this. For and while loops, we talked about those as well. Like for is for repeat interaction. So where you go, you do something over a known number of steps. This can be something that the program defines earlier, right? So you figure out, you get a data set in, you go like, this is the length of the data set with the len command, and then you know how many steps you need to do. So you don't actually need to know while you're programmed, like 10 steps. This can be something that is very flexible. While, however, is just while this statement is true. A for loop goes over a set number that you can determine. A while loop goes on until a condition is met. So, for example, do this while something is true. Then a condition is met, the loop ends. So basically something A turns to false while that happens. But you have to take care that the loop actually ends. Because while rock is not at top, push rock, this guy's still at it. So we use things like range and numpy range to actually define lists of numbers quickly and easily, right? So we can have something for loop to step through. Range is integers. Range can be floats. It is floats, but it can even be fractions of a float. So you can step through 0, 0.1, 0.2, 0.3. So you can define the step as well. The list or numpy array, and numpy array is where we're getting at, right? Numpy array is where we live as physicists, because that's where the lists of numbers, the data actually sits. So very useful to get a for loop running. And then the next thing is that I need to do something over and over again. I talked about this on Friday. I have to do the Boltzmann equation. I've done that once. I've figured out how to do this in Python. I know it comes out in this particular unit. I define it once. I put it in a function, and I can call it whenever. This is super useful, right? We do the hard thing once, and then we just have to call on it. We don't have to copy and paste. Our entire program just goes zip, lots shorter because we only have to do the hard thing and define the hard thing once. So you do define function, that's the name. So make sure that that name is not function, because what's function? What does function do? Who is function? So you have to make sure that that's a good descriptive name. And then these are the input parameters that go in there. And the return ends the function and returns a value. So if you have the phrase return in there, it goes, OK, I'm done, even if there's more later. So you can have, for example, a conditional statement. If this is true, return 0, for example. Like you've met the edge conditions or something like that. Return a particular value. And then the rest of the code can keep going. So you can have multiple returns in your code. Like your function can return particular values if edge conditions are met, for example. If dividing by 0, return minus 99, for example. In earlier days, we didn't have not a number. I'll talk about that in a minute. But we just said, OK, minus 99 is special. Nobody measures anything that's minus 99. So we'll just put minus 99 in there if it's a wrong thing. Zip. So if we say return a, comma, b, comma, c, returns 3 separate values. That's not a list, right? It doesn't, you can't pour that into one thing. It basically says these are now separate values. So a, comma, b, comma, c is my function with input, assigns these to 3 different parameters. It doesn't remember, oh, this is the other thing. If you're in a Python function and you say b equals 2, and then later in the program you go like, so I'll multiply by b, and then the Python goes, no, b was something local, only in the function. And if you didn't call the function, it doesn't matter. It's like it goes, no, that only lived in the function. It's a little sub-program. So if you then multiply by 2, Python goes, I don't know what this b person is. You don't tell me. So if you have a variable, and you want it to use it later, you have to return it. So you return these values like this, or you can put, explicitly say that this is a list of values, for example. And then you can just say a equals my function. So it's very flexible, but you do need to know what your function returns. And it has to be the same. Like if you do something like this, Python is now expecting 3 numbers to show up. Right? It's almost like a party invitation. It goes like, all right, well, I run the function myParty, and this goes in, and I'm expecting these 3 to show up now. So if you return 2, then it's going to go like missing 1 value, and it's going to throw an error. We have the unnamed function. This is back when we went through a slide to Harry Potter phase. That's the lambda function, right? This is the reason that we don't use lambda as a variable name. But that's so why we do that. It's just a quick function to be used in a call of a larger function, for example. Use sparingly. I don't use it at all. Other people do because it nicely condenses code. It becomes much denser code that way. And yeah, sure, if you have 10,000 lines of code, I can see that you're trying to save some space at some point, but that's later on. So the indentation is sort of the main feature of Python for me. The fact that we don't have to use curly brackets. It looks at it, how it's indented, and go, this is 1 block, this is block 2. So if I'm running this and there's a conditional statement, under conditional statement in block 1 means that block 2 is under that conditional statement. Run this. Like if there's an if, run that. And if there's another if, then run that. Right? So the amount of indentation tells you what part of the code to run. This is the main code. Like it goes block 1 continued. So if statement is not met, it goes straight here. Yeah, I know it's Monday morning, but let's make sure. So this is how it reads your code. This is a good thing to do anyway, because C code used to look like this. This is a bunch of if statement. If the username, user password new is what's a repeat. So there's a whole bunch of if conditional statements to be met. In order to have all of that neatly organized, you have to both have all the curly brackets to actually execute it, but you had a tendency to tab them in anyway so that you could read where that, like this block starts here, ends at this semicolon, so end here. This is the block that is under this if, and then ends with this curly bracket, and then an else, and then start with a curly. So why do the curly brackets? So they just drop the curly brackets. It's just the indentation. Yes? Okay. So this is the main thing for Python if you have like functions, for loops, while loops, and conditional statements. They all are tabbed in. That's how you can tell what's underneath that particular statement. Yes? Just making sure. Okay, arrays. Haha. Welcome to NumPy. NumPy is great because that's where all the numbers go, and it's always a list of numbers. It can be a list of integers, it can be a list of floats. You can tell it what kind of integers or floats it needs to be, like 64 bits or 32. A data sample or time series, you want some basic values of your data. So this is where we get to the point where my whole idea is that some professor throws you a CSV file, so a comma-separated values file, or basically an Excel sheet full of data, and goes, here, make plots, or here, give me basic statistics, right? So you get raw data in, and you go, okay, I have to do something with that. NumPy and NumPy arrays are sort of how you get the basics immediately. You can get things like mean, mode, standard deviation almost instantly, because these are built-in functions. So we import NumPy as NP. Honestly, I would encourage you to do that because everyone I know and a piece of code that I've seen published, nobody types out all of NumPy. I don't know why they simply just call it NP. So you can do things like the Gaussian distribution. Who here has actually encountered the Gaussian function, the normal distribution already? You surely have a little bit during statistics. You get graded on a curve. This is the curve, right? The curve is the bell curve. There you go. That's the one. That's the other one, right? There's many terms for it. This is, I think, one of the best physical examples of the bell curve, right? What's the typical weight everybody uses? They're sort of in the middle, and then you've got like a tapering function on either side. So you've got that bell curve up and down. This is the bell curve. Yeah. There's a mean, so mu, and then you have standard deviations, 1, 2, and 3 standard deviations away from the mean. So in one standard deviation, you've got about 68.27, so like that's where 2/3 of the sample sits in. Another third sits in the wings. So if you're one standard deviation away, you're not that far off, right? You're not that unusual. This is something that medical students struggle with because there's like a little bracket on their medical instrument, and that's this guy, right? So 2/3 of your patients should lie within that bracket, and 1/3 of them, so every third patient should be outside. That's normal, and so you shouldn't refer them to further testing if they're, outside. It's like, is this? Yeah, dude, the last two were, inside. Now, 95%, that's 2 sigma, and then 99.7, that's 3 sigma. So really, if you're 3 sigma away, that's when it starts to get, is everything okay? Right, so maybe those are the odd ones out. That's where it gets, so if you go, this is the mean. So for example, this is the mean height of 6th graders. This is the mean height of 6th graders. Now, people are fantastic. They all seem to always, if you have enough of them, they're random enough that they basically become this bell curve. So should I worry about the 6th grader that's like 2 sigma below the average height? Not really. You expect a few of them. Should I be worried about the one that's 3 sigma? Maybe there's something going on. So maybe we go to the pediatrician, right? So you expect only 1 in 100. Like, so how big is your class? This is the fun part. We always put XKCD in there, right? Because this is the greatest way to annoy statisticians. You go, oh, well, this is also a midpoint. You can get first, so assuming your data follows this kind of curve, right? Things like heights of people, shoe sizes, grades, just about anything that you have a large number of people of, then you can always get a distribution. You almost always get a distribution like that. So you get the mean, the standard deviation, the mode, and the median also drops out immediately. NumPy has a whole bunch of these built-in functions that gives you all that stuff immediately. So the mean is the average, the median is the halfway point, and the mode is the most common value. So if you look at the normal distribution, they're all sitting right here, right? So this is where this gets confusing. But if you have a different distribution, so for example, if I take and multiply this time, like 10 times 10 to the power of the log distribution, I get the log normal distribution. So that's where the most common value sits here, for example, where the mean value sits about here, and the median is, also in this range, but different. They start to get different. So if your distribution is different, so it's a quick way to figure out, it's like, hey, is this actually Gaussian, other than plotting or taking a histogram? You go like, are my mean, my mode, and my median the same? If they are, it's a Gaussian distribution. Standard deviations allow you to sort of go like, okay, well, here's my distribution, here's one standard deviation, so I have the mean, I have the standard deviation, and I have the value that I'm worried about. Is it 3 standard deviations over or under, for example? So NumPy's arrays are, you can do other things as well. You can mask out certain values. So if you go, hey, I have a temperature range, and I know that my thermometer, it says so here in the instructions, is unreliable over 150 Fahrenheit. So I should not use it. This is not an oven thermometer, so 150 Fahrenheit, it's not calibrated beyond that point. So I should say, like, mask every value out, or remove every value out. You can analyze sections, and you can quickly get general statistics. Your data will almost certainly be a NumPy array, or something that basically lives as a NumPy array. Here are 2 special values that you can find in a NumPy array: nan and inf. Nan means not a number. This is such an innovation because, it turns out sometimes you do measure minus 99. There is no special number that you can just use as a flag as well, right? If you have temperature ranges, sometimes it goes to minus 99. So it's much better to say, look, I didn't get a number here. And so that's the value now says nan. Nan means there was no measurement here, which is a piece of data, right? It's like, I don't know, I have a traffic control light with like a motion sensor, and it's like, midnight nan, right? No movement. Like there was a power outage, and it's like, that's when you want nan. 0 means no movement. Nan means power outage. So there's missing data here, but that does tell you that, something was supposed to be here. I was supposed to measure, but I got a nan. Inf is infinity, which usually happens when somebody divides by 0 or takes the logs of something negative or something like that. But you get a infinity returned. However, you can have positive infinity and negative infinity. So there is actually 2 numbers there. And so these are often things you have to filter out. Something has usually gone wrong. Like, you're not interested in infinities. That's not a measurement. Although, again, this is a number. That is explicitly not a number. Right? So you need to check for those, and there are built-in functions for that. So NumPy where returns a list of indices where the statement is in the brackets is true. So for example, if I have a temperature, I have a list of temperature values, and I say NumPy where So I have a NumPy array with temperature values, and NumPy where temperature is over 150, then it only returns where that value is met. Or below 150, for example, if I don't trust the thermometer above that. See how that works? Okay. NumPy is nan returns true false for everything in the NumPy array if it's a nan or not. So you can say like, hey, I can check for nans that way. Did my instrument drop off the grid for any amount of time? Or and so you can do that, and you have is_inf, and so you can check for those, and you can use the top one to sort of filter those out. Or you can say replace anything where is_nan with 0, for example. But then you have now measured a whole bunch of zeros, and you didn't have them before. Another fantastic thing about NumPy is random. So one of the things that if you want to simulate your own data, you want to simulate the noise that happens naturally. And that usually follows one of those Gaussian, one of those bell curves, right? If you look at the pixel values of, so if you keep the lens cap on, back in the day we had cameras that weren't connected to our phones and they had a little cap on the front. So basically if you took a dark image, you get a digital image that is black but has values that sort of fluctuate around 0. This is a very useful thing. This sort of tells you what the electronic noise of the camera is. If I'm not giving it any photons, this is what it looks like. So if I want to then generate a whole bunch of fake images like that, I can say, okay, well, I've measured what the standard deviation there is, and I know what that is. So I can say, like, around this mean, give the standard deviation. But I can also randomize. I can actually generate random numbers. If I want to do something like cryptography, and I want to add a random number to the letter code that I want to do, but I know what kind of random, like I want predictable random numbers, this is the one that you use. So if like this is the state, there's a seed state, you say like for seed state 42, just it always generates the same set of random numbers, but they are random. They are intrinsically noise. So, one more thing. You do get to Google these things. I personally really like this one. When someone on Stack Overflow already has asked your incredibly specific question. This is great, right? So please use it, because if you start coding with a new language, and I have been this person, where you don't know any of the documentation, yes, please go Google your documentation. All the documentation is online. So I'm perfectly happy if you've got Hab1 in one window and Stack Exchange or Google in the other. So that was what I wanted to introduce today, right? So NumPy random is the one that we're starting to talk about next week. That's the part where we can generate our own data. And I want you to understand that from using SciPy, but also especially NumPy. NumPy random has these distributions. So not just the normal distribution, but log normal, exponential. Anything you can think of that's a mathematical distribution, it's in NumPy. So you can say, hey, the manufacturer of the camera I'm considering buying for my scientific setup says that the read noise, the dark noise, is this with a Gaussian distribution. So it's like a 0, 0.000.1, or 0.00001, like hardly any noise, but there's a little bit of fluctuation around it. I can generate that image using NumPy and NumPy random. Like I just add random noise to it. And then I go, okay, I know that the stars that I want to look at with my camera have this distribution of light, right? So they are log normal, and it starts with 1 count and it ends with 100, for example. So that's my log normal distribution. So I can randomly pick from a distribution like that and add them in, and then see if what my camera picture looks then. So without buying the camera just yet, I can go like, okay, what should it look like? And all these things, like this is how we simulate data before we start actually building the instrument. If I put in the noise from the camera and the noise from the electronics and the reasonable noise from well, usually that's all sort of it. But like in the case of astronomy, you add reasonable noise from the atmosphere, reasonable noise from some other things, and then you add everything together and go like, hey, is this enough? How long do I have to keep the shutter open to actually measure significant amount of photons, a significant experiment? So you can actually run through the whole thing. NumPy random is where this starts. I can show you a Jupyter notebook that's literally just NumPy random calls, where that's a publication of mine, where I'm like trying to figure out how much this experiment would see. Like, okay, this follows this distribution, this is a reasonable assumption that's that distribution, and then I just do it loads of times. That's called the Monte Carlo technique. And so it's like, because computers are cheap, I could just go do this 10,000, 100,000 times for me, and just see how many of them go through all those distributions and actually make it to the end. So this is where NumPy random is such a useful tool. Good random values is something that computer science looked for a very long time, because cryptography, if you don't have good random numbers and there's some sort of pattern in there, hey, if you have enough messages, somebody's going to pick that up. So a good randomizer, NumPy is a good randomizer, will help you with that kind of thing. Okay. Any questions about today's assignment or this week's assignment, assignment 2, where we're going to go into lists, and eventually, next week we're going into NumPy and NumPy random? No? Okay. Certain there's no questions. In that case, I'm going to stop the recording. And yes?
Actually, I have one on exercise 5
yeah.
about